All right. How's everybody doing with these? All right. Uh, so so I called this was, in fact, to say George again. If you looked at his set of axioms, this was one of them. So I said, hey, that's a cool thing. We should make sure we can prove it, right? We should be able to, if he has an axiom I don't have, then we better be able to prove it. And I called it distribution. Why? Because here we kind of have a bracket with a for all on the outside. And what are we kind of doing? We're kind of distributing the for all on the inside, right? So it feels distributive to me. So that's why I called it that. But I don't know what you call it. All right. All right. So this is just trying to get some intuition about it, right? What is the how do we prove that? We assume the left side. What does the left side say? It says if you give me any x, right, and alpha is true for that x, then beta is true for that x, right? And when we were, I haven't added it to the slides, but I think it's a nice example. During the tutorial, we came up with the example. We're at a party, and alpha says this person wants to play a game, right? And beta says this person gets to play the game, right? So this line says for any person, if they want to play, they get to play, right? It's the American dream that everybody has free choice to do what they want, right? So right? So over here now, what are we saying over here? We're saying this is different. This says if alpha is true for every x, you have to know that it's true for everybody, right? This says if everybody wants to play, then everybody gets to play, right? So I think of this as more Eastern cultures where you're more community oriented. If everybody agrees on something, then you get to do it, right? Now the problem, that would be great, right? If everybody was getting really mattered. But usually what happens in those cultures is that if the man of the house wants to do it, then you're going to do it, right? If the boss, the dictator wants to do it. But anyway, here we're saying if everybody wants to do it, well, if everybody wants to do it, right, then each individual person, right? Here it says if an individual wants to do it, they get to do it. And then this says everybody wants to do it, and hence everybody gets to do it, right? Everybody buys that? So what about the other direction, right? The other direction says, what do we know? We know that if everybody wants to do it, then everybody gets to do it, right? Now, does it follow that if Bob wants to do it, he gets to do it? Right? Does this follow? No, it doesn't follow, right? Right? There could be maybe, or no, before we can get Bob to do it, we need everybody to do it. All right, so now we're going to do the two proofs. The one proof will work, right? And the other proof better not work, right? So we want to prove this. And so we have a for all on the outside, right? So we do deduction, right? And then we have, again, we could go down here and do the deduction on this, or we could remove the for all, right? You have your choice of which direction to move. So I decided to remove the for all. Why? Because it looked like all x's down here, and it seemed plugging in an x wasn't a bad thing, right? So this is still saying for any free variable x, if x wants to do it, x can do it, right? So what are we doing now? We got to do this deduction. So we're assuming everybody wants to do it. We want to prove that everybody can do it, right? And how do we do that? Well, now we have a for all. What do? Remove the for all. Now we're kind of saying, I'm assuming, back to the game, we're saying, I'm assuming that it's true for every x. All right, so Oracle, I can give you any x who I want, right? So I'm going to give you this free variable x, and she's going to assure me it's true for that x, right? And now, look at, now I have alpha x is true, and I have alpha x proves beta, right? So I can get beta, and then I can put the for all back on, right? Are people following this, right? And you can kind of, I think it's, as yeah, I keep saying the same things over and over again, right? Are these hard to prove? I don't know how hard that is to prove. Every time I try to prove one, I manage to prove it. Do I have a good feeling that I can always do it? Not necessarily, right? All right, so now we're going to try to go the other direction, right? So we have our deduction, right? And then we have right? So our goal is to prove, we're assured this. We're assured that if every alpha wants to do it, then every beta wants to do it, right? And what do we want to do now? We want to prove something. We have to prove for all x, right? So to prove for all x, what do? I say, give me an arbitrary x, right? That's kind of what we're doing here, right? We're saying here, I need to prove for all x, give me an arbitrary x. There it is, given to me by my adversary, right? And then I need to prove this implies. And you'll note how the parsing of this thing worked, right? The implies is not the outer thing. So if the implies was on the outer thing, I would have done deduction first, right? But it's not the outer thing. The outer thing is the for all. So I have to rip off the for all, right? And once the for all's ripped off, now the top layer thing is the deduction, right? So we're kind of, I talked about building parse trees where you unwind things and get a tree. We're kind of doing that here, right? We're ripping off the for all, and now we're kind of ripping off the implies, right? How do you rip off an implies? Is you do a deduction, right? So now I'm assuming x, and I'm assuming alpha of x, and I need to prove beta of x. All right, everybody get that? All right. So what? Right. I need what I need is this up here, right? So what should I do next? What should my next line be? Right? Let's put the for all on, right? So I can get this thing up here, right? And this is where I was starting to panic, right? I have, x is a free variable. I know alpha of x is true for this free variable, so I can put on the for all x, right? And now I have for all x, so I can get for all x beta is true, right? I have the left side, so I can get the right side, right? Now I have the for all. I can rip the for all off and get the beta, right? Everybody get this proof? Everybody agree with this proof? Yeah? Yeah. So the reason I would look at this proof and say, yeah, it looks like a pretty good proof, right? In fact, that's what I did, and I started panicking because I knew it's false, right? We know this proof isn't good because the statement we're trying to prove is false, right? And so that's where we have to go in and see, oops, right? What did we do wrong? And so it's the official rule we did wrong, is down here, we want for every x, alpha x gives me beta x, right? So how do we, so here we want a free variable, right? So we have to assume this and get that. But what are we assuming? Well, we're assuming it for, we're assuming it for an arbitrary x. Maybe this is the way to think about it, is I'm assuming alpha for an arbitrary x. Which x? Yeah, it's an arbitrary x, right? Oh, but now is it an arbitrary x? No, it's no longer an arbitrary x. It's the x that we assumed, right? Is this an arbitrary x? Yes. But do we now have alpha of x is true for an arbitrary x? No, we don't. We have it's true for the one x that we assumed it was true for, right? We can assume alpha of x for any x you want, but only one x at a time, right? That's kind of what we're saying here, right? So here, we're assuming it's true for some fixed x. And I don't see any difference between the exists and the arrow, but they're different meanings. So I gave you a different symbol, right? So the rule is, if the left-hand side that you're assuming has a free variable, right? Then George will tell you you have to know that x is of this case, and you can't add a for all to it, right? So here I'm saying let's not remember that when we came from the assumed, we're going to put this extra symbol, right? And once we have this extra symbol, then you can't do that, right? You can't go from it's true for the x that we've assumed to going and saying it's true for every x, right? People see that? And we're going to, later I have a different section called free variable fail. And it's just a really small example where you need to do this. All right, this is a more complicated example where you need it. Everybody kind of with us here? Right, so that's bad. All right. Any questions? How are we doing for time? 10 minutes, excellent. I think we might even be able to finish formal proofs in 10 minutes because I don't have too many left. All right. Oh, that's not true. Then we go into other weird things. Take that back. We won't finish it in 10 minutes. All right, so let's think about what this, now we're distributing again, right? We're distributing the for all over this and, right? And so we want to know, can we do that or not? Can we distribute it one direction? Can we do it the other direction, right? And I was just making, we had one distributive law, so I made up some others, right? And this one, remember earlier when we first talked about for alls, it's kind of like a big and, right? So it's kind of asking, can we distribute and over and? And can you? Yeah. A and B and C. You can put the brackets wherever you want, right? So this should be nice and good because we're just distributing and over and, right? Oh, yeah, that's what I say. They're both effectively and, right? So what does this one say? It says for every x, we have both of these, right? You give me x, we have both of them, right? So what do we know? Well, they're all true, right? We're doing it row by row. They're all true, right? And what are we doing over here? Well, we're kind of doing it more column by column. Right? This guy says what? Says we have this column, right? And what is this side? This side says we have that column. So we did it, one we did it row by row, one we did it column by column, right? And similarly, here we have an exists is kind of like an or, right? So can you distribute ors over ors? Certainly, right? What does this say? This says there exists some row, and then, right, oops. It says one of those is true, right? I don't know if my notation is my picture is very good, but right, this says there exists a row, there exists something in this row. So there's a somewhere in this matrix, right? If I tell you there exists a row and then there exists the column, it's the same as there exists the column and there exists the row, right? All right, so how do these proofs go? Well, I guess I haven't done the deduction backwards, but here it's right. We assume the left, and then we rip off the for all, and then we separate the and, right? And right, which is in the purple slides if you haven't looked at the purple slides. And then you put on the for all, right? And then you get the beta from the other side, right? And then you put on the for all, and then we have the for all alpha and the all beta, so we can build, right? And let me tell you, in case you care, on Thursday I looked at this, and it had different words here, and that's because I made these slides before I made the purple table. So I went back and purple tabled it. Everybody good? So that was pretty easy. Going. Oh, here's a funny thing. So now we want to prove the other direction, right? And some rules go both directions, right? Right. So if A and B are equivalent, right? I say you can go from A to B, then you can go from B to A. So some rules are like that. And some rules are weakenings, right? I can go from this strong statement to this weaker statement, but then I can't go back, right? Because I've weakened it. And all of these were if and only ifs. So we can just take the exact same proof and go backwards, right? So you can see that all of these rules go backwards, right? Everybody buy that?